the hydrogen molecules of the last three groups of the periodic table. So things like NH3 and the ones below it, so pH3, that sort of thing. And what we're looking at is what happens, the relationship between their molar mass and their boiling point. And what do we notice is the general trend with these? What's the general trend you're seeing there between molar mass and boiling point? The larger the molar mass gets, what? The lower or the larger?
The higher the boiling point.
Higher the boiling point, okay? And we do need to be able to explain why this is the case. These are all molecules. None of these are ionic compounds, okay? So we're looking at things that are molecules. There are forces between these molecules called intermolecular forces. You might have heard the word Van der Waals or London forces or dispersion forces. They're all the same thing, kinda. Because we're going to throw you a new one this year that isn't one of those, and it's a special type. And the reason that we weren't given values for HF, H2O, and H3 in our graph was because they break the trend, and you wouldn't have seen the trend if they were there, possibly. We need to be able to explain the strength of intermolecular forces by looking at the boiling point. So a higher boiling point implies a stronger intermolecular force. So the forces between them are stronger, or there are more of them. But because of the types of molecules these are, it just means they're stronger. Okay, they're not really big macromolecules like plastics. There's lots and lots of intermolecular forces. So when we look at what affects intermolecular forces, or what affects their strength, we're looking at two things. One is the size of the electron cloud, and one is the polarity. I'm going to actually start on the right-hand side, because this links to the activity you've just done, where you found the larger the molar mass. So as molar mass went up, so did the boiling point, which means the strength of the intermolecular forces went up as well. For those doing physics, you could change it to be this relationship. Molar mass is proportional, not directly, but it's loosely proportional to boiling point. As one gets bigger, so does the other. There is a reason for this, and it's to do with molar mass linking to the number of protons linking to the number of electrons, the number of electrons having a direct relationship to the size of the electron cloud. I'm not going to use the ones from your activity because they've got hydrogen in them. I'm going to use the halogens as my example. Fluorine and chlorine are both gases at room temperature. This implies that their boiling points are below room temperature, because they have already had all those intermolecular forces broken. This means, or implies, sorry, that their intermolecular forces are very, very weak. Bromine at room temperature is a liquid. That implies that there are still enough forces there, intermolecular forces, that room temperature does not have enough energy to break all of them and therefore evaporate it. However, you might notice that whenever we use bromine, we use the fume cupboard because it does evaporate quite easily. This is because even though there are enough forces there to hold it in the liquid phase, they're easily broken because it's what we call a non-polar molecule. Iodine is actually a solid at room temperature, but if you give it just a little bit of heat, it sublimes. It doesn't even become a liquid. It turns into a gas immediately. But again, it's got therefore stronger forces than bromine between the molecules. Bromine has stronger than chlorine and fluorine. And by the way, if we got to low enough temperatures, we'd find that chlorine liquefies before fluorine does. So this is our smallest molecule, because as we've done in our radius of atoms, fluorine atoms are tiny. So two fluorine atoms together are not very big either. So this has got the smallest electron cloud. Whereas iodine, with its valence electrons in the, I have to check quickly, fifth energy level, is really big. So therefore two of them is really, really big. What that allows for is the probability of those electrons in that big cloud to be evenly distributed becomes smaller. The probability of them being evenly distributed becomes smaller because of the large electron cloud. Therefore, it's more likely that actually the electron's a little bit closer to this iodine or this iodine at any instant or moment in time. This creates an instantaneous dipole that then can create a dipole in a neighbouring iodine molecule. So it creates a chain reaction which allows iodine to form lots and lots of intermolecular forces that are weak, but there's so many of them that it's a solid. Bromine's got a smaller electron cloud, so it's got a higher probability of everything being evenly distributed, so therefore not having many forces between the particles. That's why it's a liquid at room temperature. There's enough energy to break the forces that are made, but then it's not hot enough to stop them reforming again. So it becomes a liquid. Break, remake, and so on. Chlorine and fluorine are so tiny that actually at room temperature, they move too fast, so it's got to the size as well, they move too fast, and the probability of an uneven electron distribution is so small that actually at room temperature they can't form bonds between the molecules, intermolecular forces. So, how do I show that? I want to show iodine because it's a good example, and it's nowhere near to scale, but if I've got an iodine here, here's its electron cloud. At any moment, it might not have perfect distribution of electrons. At any instant, this side might be delta minus because the electrons, one of the electrons is a little bit closer to that iodine than to this one. Just one of them. With that many electrons, the probability is quite high. If this side is delta minus, this side must be good. You must have a dipole being created because it's a molecule, no charge. Then, at that instant, it comes nearby another one. Well, this delta minus side has an impact on this electron cloud. What do electrons do to each other? Repel. So it will push this electron cloud that way just a little bit, but it's enough that it's no longer symmetrical, which means it induces a delta minus there and therefore a delta plus on this side. This allows for an intermolecular, I want to use a different colour there, sorry. An intermolecular force can therefore be formed between those temporary, they don't last forever, between those temporary dipoles. Shouldn't have not done it that way either. So there is a temporary dipole formed between them. A little bit of heat and it will break, and this induced dipole will disappear, and this one might even disappear as well, and they become non-polar again. Okay. So that's the effect that electron cloud can have. If it was a smaller electron cloud, the probability is that it will stay perfectly non-polar for a longer period of time. The chances are the electrons, because there's fewer electrons, the electrons will be evenly distributed for more often than not. This is why you did molar mass, because molar mass determines electron cloud size. The bigger the electron cloud, the more chances you'll get of what we call temporary dipoles, which is why I've got the link between the two there. So therefore, polarity must have some impact. Well, the ones you did the graphing on, most of those are polar molecules. In fact, I'd say all of them are, technically, because they would have uneven distributions of electrons. They would have dipoles that don't cancel out. So, because they are polar, and can I just have one example from the graph that you did have to plot? Any molecule. I don't mind which one. NH3. Oh, right. Was that one you had to plot, though, or did they not have the value?
Oh, sorry.
One that you did have the value for.
S2H.
S2H. H2S?
H2S.
Cool. Brilliant example. Love it. So H2S is much like H2O, actually. This is a really good one to use. So H2S H2S has got 4 regions of electron density. It's got these 2 polar bonds, and so therefore it's a polar molecule. I'm very quickly trying to remember my electronegativities of these. I'm going to presume that sulfur is more electronegative than hydrogen. I may be wrong, but the details aren't important. That would create a delta minus and a delta plus. Though that dipole, so through the centre of the molecule, that dipole is permanent. It's always there. So when this comes near another H2S molecule, it creates one of these attractions, Van der Waals forces, or whatever we want to call them, intermolecular forces, between the two molecules. They are stronger because they're always there, whereas in non-polar things like I2 and so on, they come and go. These are permanent, so it creates a permanent dipole force. So the neighbouring H2S that bonds to this would be oriented this way to allow for the bond to form here. And this is why H2S would probably have a relatively, for its molar mass, which is very low, it would have a relatively high boiling point and melting point. Right. Just going to close that door. So polarity and electron clouds have an effect. But then in your graph you were given 3 other molecules which you were not given the values for. And if you were to look at the shapes of the graphs, you would expect that these would be the 3 lowest values in your graph. If you were to follow the trend towards the y-axis, you would expect them to be the lowest values, I would expect. However, we know about water, for example, that would be way up here. This is because another thing is happening. This is not just polarity or electron cloud size that are being involved. This is another type of bonding that is brand new to you this year. This is called hydrogen bonding, and it is a very special bond because it is very strong. It is about roughly 10% the strength of a covalent bond. So it's nearly the strength of an intramolecular bond. So it's very strong. And it explains a lot of real-world things. I'm going to use H2O because it's the molecule we know pretty well, water. Okay, if we look at it, it's got these dipoles for the bonds, creating a polarity for the molecule. However, you'll notice the way they line up isn't just with that slotting in here, with the delta minus lining up the delta plus side. You've actually got a lone pair lining up with this delta plus. The reason is oxygen and, by the way, fluorine and nitrogen are so strongly electronegative that it allows for a hydrogen bond to occur between that lone pair and that hydrogen. Now, if I just quickly show you something, what ion is that if that came off?
H plus.
Basically H plus, but it's bound to that, so it'd be H3O plus. Now, remember last year, that's what we told you H plus really was. That's close to true. Okay, and what will be left over? OH minus. So you can hopefully see how water dissociates itself so easily. The hydrogen bond exists, so really would it take much more of a push for that just to belong to that one and be detached from there? No. So that might help you understand the dissociation of water a little bit. But as well as this is really strong. Way, way stronger than this, which is way, way stronger than this, actually. Okay, mainly because they're always there, they come and go. But this is so much stronger. And this explains why water boils at 100 degrees in standard conditions, standard pressure, etc. This bond is hard to break. At room temperature, they break and remake quite easily, which is why it's liquid. But for them to be broken, you need heaps more energy. So water molecules often don't flow as individual molecules. They flow as groups of molecules. Okay, dimers, trimers, so 2 units, 3 units, that sort of thing. They actually flow as groups. But because they're so tiny, it's still a liquid. They're not a solid. When it becomes a solid, by the way, this bond has a particular length. It has a particular length. And so when you freeze water, liquid water, it makes heaps of these hydrogen bonds, one for every lone pair and one for every hydrogen. And therefore creates your three-dimensional crystal a lot like diamond, actually, which explains a couple of things about ice. One is that ice is really hard. You shouldn't chew it. It can actually break your enamel. It's stronger than enamel if it was to slice. But also why ice floats. As a liquid, these particles can flow past each other and get very close without bonding with each other. But in the solid form, it expands out because these bonds have a particular length. So it can no longer flow. So it takes up more space for the same number of particles. So therefore the density decreases. If it were not for hydrogen bonding, ice would sink. If ice sunk, then I don't think you'd have much fresh water on the planet, because icebergs would sink and at the bottom of the ocean, not float at the top. And it would also mean that it would sink at the bottom of lakes and so on, which would allow salt to collect in them. So the fact that hydrogen bonding exists is one of the key things as to why life on this planet as we know it can exist. Alright, so start with something as lame as graphing, end up with understanding hopefully a little bit about some types of forces that actually explain something about why ice floats, the size of the hydrogen bond, why water boils at 100 degrees, not at negative 100, for example. And therefore, these are the types of forces that actually allow life as we know it to exist on this planet.